Module we are learning about diodes. We need to know the symbol because we will see diodes in our circuits like you see resistors, capacitors, inductors. Now you know how to identify them, and you know how to identify a voltage source, a current source, dependent sources, independent sources, resistors, capacitors, inductors, switches. So these are like, there are symbols for all of these ones. So here we need to know the symbol for the diode as well. And as you see, the diode symbol will look like this. So diode is like a switch, and it lets the current to flow in one direction. It is not letting the current to flow in the opposite direction. So it allows current to pass in one direction. So it's always let the current to pass through this direction only. So it is letting the current to go through this direction. So when the current is going to the other direction, it is not letting the current to go through. Okay, so when it is in this direction, when the current is going in that direction, we call it is forward bias. And if the current is coming from this side in a circuit, we call that the reverse bias. Do you understand what I mean? So when the diode is in the reverse bias, it's like a open switch. So because see, if you look at this one, this voltage source is supplying a current in this direction. Am I right? Because the current is coming out from the positive side of a voltage source, but the diode is in the reverse bias, and it is not letting the current to go in this direction. So it's like an open switch. Do you understand that? And here if you look at this one, the diode, the current is going like this, like in the previous one, but the diode is in the forward bias, so it let the current to go through the diode. So it's like a closed switch. Any question up to here?
So if it's like that,
it's always let the current to go from this end to the other end. It can be like this, or it can be like this. It doesn't matter as long as your current is coming from this side. This is like a barrier. So when the current comes to the barrier, it's not letting the current to go through. It's like open switch. It's let the current only going from this flat end here, from this triangle, not to the tip of the triangle, the base of the triangle. Makes sense? So when you do few questions, you will get used to that. Let's see how it is constructed, the diode. So we know from your engineering materials. Have you done engineering materials? Introduction to engineering materials. Okay, so you should have remember the electrons, protons, and those kind of things. You don't need that much, that knowledge here, but for understanding, we need to know a little bit knowledge about the number of electrons around the at the outermost shell, valence electrons. So the Bohr model of the atom is that electrons can circle the nucleus only in specific orbits, which corresponds to discrete energy levels called shells. So the atomic number is the number of protons in the nucleus, and for an atom, the number of protons are equal to the number of electrons. And the outermost occupied shell is called the valence shell. So you have learned that in engineering materials. And the electrons in the outermost shell, that we call the valence electrons. So we need to know how many number of valence electrons in your outermost shell for any element. You can find it just by looking at the periodic table. To understand how this diode works, we need to know a little bit of this electron configurations, not to a depth, okay, just to understand. But after that, for answering questions, actually you don't need to know this, but we just to have a complete knowledge, we need to know a little bit of it. So depending on the number of electrons in the valence shell, we can divide materials into three groups: conductors, semiconductors, and insulators. So when we have valence shell, means the outermost shell. So when we have 1 to 3 electrons in the outermost shell, it is a conductor. And when we have just 4 electrons at the outermost shell, we call them semiconductors, and when we have more than 4 electrons in the outermost shell, we call them insulators. So when you look at the periodic table, you know this because it is arranged in a way the column number gives us the number of electrons at the outermost shell. So if you go to this one, so you can, this is our D block, and this one has 1 electron at the outermost shell. This one has, this whole column has 2 electrons, 3 electrons, 4 electrons, 5, 6, 7, 8, like that. So these are the semiconductors. Makes sense? Because these are the materials which has 4 electrons at the outermost shell. So the ones here they are conductors, and the ones here, because they have more than 4 electrons at the outermost shell, they are insulators. Okay, now let's see. When we consider silicon has 4 electrons at the outermost shell. So when you look at your periodic table, you will see that it is in the 4th column, which I have showed you. So they are staying like this. If we have something with 1, 2, 3, 4, 5 electrons, and if we have an impurity here, what is happening is 4 electrons can be stayed or have bonds with 4 electrons of silicon, but there is an additional electron. Do you understand that? So in that case, so you can see here, because we have an additional electron, we call that an n-type material, n-type semiconductor. Because why? We have 1 electron additionally. Makes sense? Similarly, when we have an impurity with 3 electrons at the outermost shell, so you can see here, we have boron and it has only 3 electrons. So when you have boron as an impurity, what is happening is 3 electrons can be bonded with the 4, like we have 4 electrons in silicon, but one, like there is an additional hole here, space for an electron, because there are 4 electrons at the outermost shell of the silicon and the 3 electrons at the outermost shell of the boron. Do you understand? So here you can see silicon has 4 electrons at the outermost shell, but boron has only 3. So there is a space for an electron to stay. So this kind of a material we call p-type material. So n-type and p-type materials. Have you done that in? I think you should have done that in engineering materials. No? Okay. I'm sure you should have learned this. But that's okay. To do the electrical questions, you don't need it. But to understand what is a diode, we need to know a little bit of. I'm not going to ask this kind of questions in the paper. But for your understanding, it is better to know these things. Okay, so what is happening is when we have a p-type material and an n-type material, so p-type materials have holes or spaces for electrons, and n-type materials have additional electrons. So when we keep these two materials together, what is happening is these electrons are starting to move to the spaces. So there is, like, occupied this hole. So this area here is the depletion region where the electrons have moved to the spaces in the p-type material. So they are migrating electrons from here to here. So this is how a diode will look like. So in the diode, actually you have this depletion region and a p-type material and an n-type material. So if you symbol of a diode, it is like this. So you can see at this p-type, the electrons can move from here to here because these are the electrons and these are the holes, and you have a depletion region. So the electrons can't move from the n-type to p-type, but electrons can move from p-type to n, because electrons will move like this. Makes sense? If we connect a diode to a circuit, it is happening like that. Okay, because of the depletion region, so there is a, I'll show you the ideal condition and the practical condition of a diode. So ideal condition, we consider there is no depletion region, no else there is no voltage drop across the diode. But in the practical situation, if we have a silicon diode, because of the depletion region, there is a 0.7 voltage drop, and we consider it as a constant value. However, in the real case, this 0.7 is not a constant, it is changing with the current. But you don't have to deal with this in your questions. You will either get questions with ideal situation or a practical situation. So what do you need to remember is, when you have an ideal diode, there is no voltage drop across the diode, but when there is a silicon diode, there is a voltage drop of 0.7 volts in across the diode. You only get silicon diodes. Okay, so we'll do a question, then you will understand this. Any questions so far? Do you guys have any question? No question. So I will move to the next part. Okay, so let's do a question so that you will be able to understand what I am saying. So this is a question. So you also get something like this in your exams. So using the approximate characteristics for a silicon diode. So silicon diode means whenever you see a silicon diode, that means across the diode you have a voltage drop of 0.7 volts. Determine the VD, ID, VR, the circuit below, perform the same to ideal. Okay, so let's do the part A. Only thing that you need to know is there is a voltage drop. VD is 0.7. Why it is 0.7? Because it is a silicon diode. Am I right? The rest, all the equations that you normally apply, KVL, KCL, everything will be the same. So they are asking you to find these unknowns. Okay, can I give you a few minutes for you to try, or do you want me to do this one and let you to do a different question? You try first. You only thing is VD is 0.7. Okay, so that's the only difference you have. You have a diode. You know about the resistors, you know about the voltage sources, you know about the current, you know the Ohm's law, V is equals to IR, you know how to apply KVL around the mesh, you consider the algebraic sum of the voltages. When you apply that, VD will be a 0.7. Can I, yeah, I'll give you a few minutes for you to try, and I will do after you try. 0.7 volts, yes. If it is silicon. If it says ideal, 0 volts.
So we're only dealing with a silicon diode.
Yes, only dealing with silicon or ideal situations. If they say ideal, in the part 2 they are saying it is an ideal diode. Then you don't, VD is 0. In the previous one, A, it is a silicon diode. And also you need to look at, first thing that you need to do is check whether the diode is in the forward bias or the reverse bias. Can you tell me, is this diode is in the forward bias or the reverse bias? Forward, because the current is going to the triangle, not to that barrier side, isn't it? So there is a current flow. If the current is coming into this side, it is forward bias. The diode is only let the current to go like this. Switch is closed only like if it is like that. The current is going from this end. If the current is coming from the other end, it is not letting the current to go. So it's like we call that the reverse bias, and it's like open switch. If it is open, there is no current across these resistors as well. So there is no VR is 0. So you need to first make sure whether the diode is in forward bias or reverse bias. So this is in forward bias, so you can do other calculations and find out. So I'll give you a few minutes, okay? So what is your VD? 0.7. Okay, so that's right. It's like, it's a known thing. So VD is is 0.7 volts. So I told you a few minutes ago. Now to find VR, what can we do? You can apply KVL to this mesh. So if you apply KVL to this one, you start at a point and you go around here. So you have a negative 30, am I right? And you have a positive VD and you have a positive VR. Coming back to the start point, and this is equals to 0. So you can find VR, which is equals to 30 minus VD. Am I right? 30 minus 0.7, which is equals to 29.3 volts. Are we good? Any question? You can find ID if you consider this voltage here. VR is equals to ID times 2.2 times 10 to the 3. V is equals to IR, isn't it? So the only thing that you don't know there is your ID. Make sense? So you can find ID, which is equals to VR, which is you found 29.3 divided by 2.2 times 10 to the 3. So you can find this one, and you can find ID maybe in milliamps, because we have 29.3 divided by 2.2. So what do you get for ID? What's that? 13.3 milliamps. Okay. So are we all good? Are we good? So part B will be what? You can do the part B now. The only difference that you have in part D is your VD ideal condition. So the voltage across the diode is, we consider it as 0. So your VD is 0. The rest of the things will be like, you can substitute VD as 0. Then your VR is 30. Am I right? Then your ID is 30 divided by 2.2 milliamps. I'll give you a few minutes for you to work it out. It's diode questions are really easy. VR is now 30 because your VD is 0. Isn't it? Ideal situation, your VD is 0. So when your VD is 0, your VR should be 30. And ID should be 30 divided by 2.2 milliamps. Ideal means you don't have a voltage across the silicon diode. Ideal diode means you don't have a voltage across the diode. Whenever they say silicon diode, it has a 0.7. So no voltage across the, you assume as no voltage across the diode. You consider it at 0. It's just an idealization. It is just an assumption, like, we don't have 0 volt diodes in practice, but like, just to make things easy, sometimes we have ideal conditions, like, am I right? They are assumptions, so we assume there is no voltage, we ignore it. 0.7 is a very tiny little voltage, so we ignore it. Okay, so when you finish, let me know, okay? Okay, I want you to try these 3 questions, and after you try, I will do it. And first thing is to recognize whether the diode is in the reverse bias or the forward bias, and you need to find, what do you need to find? You need to find the I. So there is a I in blue in all 3, so you have to find the I, okay? I'll give you time, and when you finish, let me know. Okay, so they are not saying ideal, they are saying approximate equivalent model. That means the diode, you consider it as silicon diodes, and you need to give 0.7 volts for the voltage. Make sense? If they say ideal, only it will be ideal. All the situations you have approximate equivalent or else silicon diode or something like that. If you don't see the word the ideal, then you have to consider it as 0.7. It says approximate equivalent because we consider 0.7 as a constant, but in real case, actual case, 0.7 also changing with the current. But you don't have to consider that voltage, changing voltage. You have to consider only 0.7 when it is a silicon diode. If it is ideal diode, it is 0. That's all. Are we good? Okay. Okay, let me see what you have done. First one, can you tell me the diode is in the reverse bias or the forward bias? How do you know? So where the current is going, starting from where? Current is starting from here, right? Because this is your positive side. So the current should go in this way. Can the current flow in that direction? No. So your diode is in open. So reverse bias. Reverse bias means there is, like, diode is not letting the current to go in that direction. So there is no current flowing in the circuit. Make sense? So your I is 0 because it's like open switch. So no complete circuit there. Circuit is open at the diode, isn't it? Am I right? Okay.
What the I with the arrow?
That is the I you need to find. So what should be that I? I should be 0 because there is no current flowing.
This one,
There is no current at all for the direction. They are asking you to find a current across the resistor, but in this direction or whatever the direction it is, there is no current actually. So your I is a 0 here. Make sense? Okay.
So if we're looking, if I'm trying to find if it's a reverse or forward, we have to look at the voltage.
You have to look at, yes, you have to look at the direction of the voltage source, and you need to find out from always from the voltage source, the current is going out from the positive side. If it is discharging, only when it is charging, for example, your phone battery is discharging energy, isn't it? But that means the current is coming out from the positive side. When you put this in charge, what is happening? It's consuming energy. Then only the current is going into the positive side. So all the other times, any voltage source is supplying energy, so the current is coming out from the positive side. So
we're not going to look at the given direction for current.
They haven't given any direction for current. They are asking, this is a question. Am I right? That is your question. Okay, so this first one, I is 0. Do you have any other arguments? Like, do you agree with this or not? If you don't understand, you have to tell me. First thing I told you, you need to find out whether don't forget about this. This is something that you need to find. Before that, you need to find whether the diode is in the forward bias or the reverse bias, isn't it? Before answering the question, you need to figure out whether the circuit is closed or open. Positive or negative what? Flow is always starting from the positive side. Not going. It's not. There is no current at all. Yeah, we think if there is a current, it should go like this. But there isn't a current, because to current to flow, there should be a closed path. Even though if we start, current should come out from the positive side, we are just saying that to make it easy for us to understand. But there is no current at all, because to current to start and flow, there should be a closed path. There is no closed path in this case. Make sense? Okay, so how about the second one? What is happening if there is a current should come out from this side and it is going all the way up to here. Am I right? When it comes to here, it can split. It can split only if your diode is in the forward bias. Is the diode forward bias now? Yes, so that the current is splitting. In case if you have in this way, the current is not going through that branch, middle branch. Whole current will be going this way. So this is like open branch. But here because of the diode is in the forward bias, the current is splitting. Understand? Current is splitting and going. Makes sense? Okay, so how can we find the current? You can do current division, but the thing is, for do the current division, there should be two resistors in parallel to each other. Are these resistors parallel? They will be parallel if you don't have something here, isn't it? So yes, so to become two parallel resistors, there should not be anything else between them, isn't it? So we have something in between them. So we can't consider, but you can apply KVL. You can apply KVL to this mesh. So you start at a point and go here this way. So that will be, what is that? 20 times I. Am I right? And when it comes here, that will be 0.7. Am I right? And this will be a negative 20 is equals to 0. Agree? Can someone answer that question?
It's because of the silicon diode. It's always going to be given as 0.7.
Okay. That's good. Thank you. Yes, that's true. So what will be the I in this case? 20 minus 0.7 divided by 20. Is that right? Any question? So they are not hard. The thing is, you need to understand what is a diode and how it works, isn't it? How about the third one, C? You have two diodes. So the current, is there a current flowing in the middle branch? Can a current flow in the middle branch? No, because the diodes are opposite. So even though if there is a current, this one can let the current to flow, but this one is not. One is in the forward bias, the other one is in the reverse bias. So this branch is open. Agree? So the current here, I is equals to 10 divided by 10, isn't it? Because the whole current is going this way. There is nothing in middle branch. We can ignore it because that is open. One diode is forward bias. The top one, you can consider it as forward bias, but the bottom one is reverse bias. So it is like an open switch. Reverse bias means it's no connection. Makes sense? So your current in the third one is 1 amp. Any question? Can I move to the next one? Okay. Okay, I want you to try this one now. I'll give you, you need to think a little bit, but you can do it if you think. I will give you time. It's okay to go wrong, but I want you guys to think. Yes, you have a higher voltage in one side, positive 20, and it is going to V0 and it is going to 0. Am I right? So here the voltage is 20, and then it is, when you come across this, it is 20 V0. So, and this is 0, isn't it? Ground. It's like you can consider this as a, like, like this. Agree? If you want to, otherwise you can just leave it as it is. So you have a higher voltage 20 at this side. So if this is higher, current is always going from higher to low. So when it comes to here, the voltage is dropping. Do you see that? It's going to 0. This is earth, isn't it? So voltage dropping from here to here. So you have a 20 volts, and then what is happening? Yes, so you have a 0.7. So is it 0.7 or 1.4? Why is that? It's in parallel, yes. So you need to understand them. Both are parallel to each other, and this one should be 20 minus 0.7, isn't it? Because you have a just 0.7 drop. If they are in series, then you have to add them together. It will be 1.4. If two of them are in series in the forward bias direction both. So V naught you can find, which is 19.3 volts. Now you have to find the current as well. So ID current is, if ID current is flowing in the top one, there should be equal current flowing in the bottom one, because the voltage drop are both the same, isn't it? So ID current also should be there at the bottom line, isn't it? So when it comes to here, the current going from this way will be 2 times ID. Agree? Do you agree with that or not? If there is ID current from the top branch, there should be a similar current, because the voltage is the same, isn't it? And you know, there it is, you don't have any resistor. If you have a resistor, yes, the current may be different, but here you have the same conditions in the top and the bottom, so both should have the same current flowing, isn't it? So that will be 2ID. So if you consider the voltage here now, voltage here, the voltage V naught minus 0 will be the voltage. Agree? Because this is 0. So that voltage divided by the resistance, which is 4.7 times 10 to the 3, will be your 2ID. Do you agree with that or not? Voltage across the resistor divided by the resistance will give you the current going across the resistor, isn't it? Is that right? So you can find the ID, which is equals to 19.3 divided by 2 times 4.7 times 10 to the 3 milliamps. Sorry, amps. And you can get rid of this 10 to the power 3 and you can make it to milliamps. 19.3 divided by 2 times 4.7 amps. Are we good? Yeah, I want you to try the second one. Okay, so now you can think of the second one and I'll give you time. It's okay to go wrong, but I want you to try this. So what can you say about the diodes? Are they in forward bias or reverse bias? One, yes, they are in opposite direction. One is forward bias, the other one is reverse bias. So reverse bias means it's like open switch, so you can ignore that path, that branch. Am I right? Which one is in the reverse bias? This one? Yes, so your current is going like this. Am I right? Is that right? Okay, now what can you say? The whole way you have ID current. Am I right? So V naught should be what in this case? 15 minus 0.7. And the voltage across these 2 points will be what? 14.3 minus 5. Am I right? The voltage difference is the V naught minus 5. Am I right? So this voltage divided by the resistance, which is 2.2 times 10 to the 3, will be your current, which is ID, because the same ID is going here. In the previous one, it was 2ID, because the two IDs are joining together at a point and they are flowing like a 2ID here. But in this case, this one is one diode is reverse bias, so the same current is flowing. They all are in series with each other, isn't it? So the current ID is equals to 14.3 plus 5 divided by 2.2 milliamps. Agree? 19.3 divided by 2.2 milliamps. Do you agree with that? Does that make sense? Okay. So any question? Yes.
So the voltage is now from 15 to
Going to negative 5.
okay, goes to the negative 5.
Yes.
So the V naught is equal to 15 minus 0.7, right?
Yes. Because, yeah.
I think that the voltage go down and it's straight out, right? It's straight
Splitting where?
At the
It is splitting, yes, it is splitting, because splitting means this. So 15 voltage is here. Then there is a voltage drop of 0.7 here. So when it comes to here, that will be this point, that voltage will be 14.3, because the 7.7 is already like dropped at the diode. Then when it is going from here to here, another drop will be there, which is 14.3 minus 5. Why it is dividing by 2? That's what I told you. Here you have ID current in this path and also ID current in this path, and both the IDs are going this way. So you have a 2 ID flowing across that resistor. But in this one, the same current, ID current, is going this way, isn't it? There is no another ID is connected to this. In the previous one, it was 2 ID because you had ID current from the, both the diodes were forward bias. So current is flowing from both the diodes equally, because both the conditions are the same. If there is 5 amps going up, there should be a 5 amps going down, equally divided. So whatever the current coming here is equally divided. But in this case, whatever the current comes is going only across one diode. Now the diode is reverse bias. Make sense? Any other question? Do you need more time? I'll give you more time. If you have, if you can think and do by yourself and ask questions if you have any doubts. So we can find V naught and also the ID. Let's move to the next one. Okay, we did this and we got that, and we did this one as well and we got this. Okay.
Is that like test question back or?
Yes, you get questions like that. Okay, but the diode questions are two parts. One is the previous one and the other part will be this. Diode under AC conditions. Before we were discussing about diodes under DC condition, now the diodes under AC condition. So you see what is happening here. Diode is letting the current to go in one direction. So when you have a AC current, means current is changing the direction, isn't it? So when this half happens, now you have to tell me. This half happens means current is going this way. So your diode is in the forward bias. Am I right? So your current is going like this. So there is a current there is a voltage across the resistor. Am I right? Voltage is the current times the resistance. So there is a voltage across the resistor as well, because there is a current flowing. So if the current is flowing, there is a voltage across the diode, across the resistor. Now when this half happens, what is happening? Current should go in this way, isn't it? Can the current flow in this way or not? No. Then there is no current flowing, there is no voltage. So when this half happens, voltage is 0 across the resistor. Am I right? Again, when the positive half happens, there is a peak, but when the negative half happens, there is a 0 voltage across the resistor. Do you agree with that or not? When the diode is in the reverse bias, there is no current flowing. Am I right? Current is flowing only when the diode is in the forward bias. So diode is in the forward bias only when the peak or the positive half happens. Am I right? Any question? If I change the direction of the diode, can you draw this one now? Okay, now I'm changing the direction of the diode. Now what is happening? No current, no voltage when you have the positive. So this is 0. Then what will happen? Yes, so if you are looking at the voltage in this or the current in that direction, this will be a negative one. Am I right? And it should be like this, isn't it? So do you understand it? Okay, that's good. So this we call, like, when we have when we have a diode is doing a rectification. That means, like, you know, we have AC current coming out from the wall socket. We don't need the AC current. Some equipments are not performing with the AC current. We need to convert the AC to DC, isn't it? So AC to DC means we need to convert this to something like this. So this is on the way, like, you know, if you can make this, we call the half wave rectification, because you only see a peak for a half of the cycle. So, but if you, sometimes we can arrange the diodes to get the full wave rectification like this. We are going to look at it in the next slides. So then this one can be converted to DC. So to do the rectification, one of the elements that we can use are diodes. Do you understand? Okay. So let's move to the next one. Okay, so what is happening here? I want you to think and draw. So your input is this, okay? Sinusoidal. So can you tell me the output? I want you to think and do it. This is the voltage, and find me the voltage. I will give you time, and then I will do after you try by yourself. You have to think.
This part will actually just draw the graph.
Yes, yes. Just drawing a graph, and this is a transformer. You haven't learned about the transformer. Don't worry about the transformer. Just think that you have a positive half happening. The current is going that way. Negative half happening. When the negative half happens, current going in the other way. You think and try to do this. If you can't, I will help you. So you have to listen carefully. So why? What's the issue with this? Okay, now you need to answer these questions. Okay, if you don't understand, I need to figure out why you can't understand. So when the positive half happens, this one happens. So your current is going in this way. Your current can go that way, and like it's going here. Am I right? It cannot go this way across the diode because it is reverse bias if it is going like that, and it should go like this. Am I right? Is that right? So there is a current going down here. Am I right? When the positive half happens, so you will see a voltage here as well. When the negative half happens, what is happening? So negative half means it is going in this direction now, the green path. Am I right? This diode is forward bias. It is letting the current to go. Again, when it comes to here, it is not letting go towards the other diode because the diode is in the reverse bias. Am I right? So the current should go in this way. Again, you can see another current in the same direction going back. Yes, going back to the same point, isn't it? So you can see another peak here. Agree? Am I right? You have to draw this, yes. Yes, we haven't done the equation part yet. But you first, to do the calculations, you need to first should know how to draw this, what you get. Do you understand that we get the full wave rectification here? In the previous one, it was half wave, but this one, the full wave rectification. What's that? Because the current is in the same direction. Always positive, yes. If it is going in the opposite direction, yes, you get the negative side. But the current is always positive, so there can't be any difference in the red peak and the green peak, because both the same. Even though the green peak is this, it is the minus side is at the input. It's still giving you a positive side in the output. Make sense? Any question? Yes.
Oh, could you show me how the current is going to be if this is the negative current?
For have the negative current, we need to change the circuit. So we'll see whether we can. Look, our purpose of having the diode is to rectification. We don't purposely we are putting the diodes in a way that you get in the positive side. So why? I told you AC, we need to convert it to DC for some equipments. So diode is used to make this rectification in the process of converting the AC to DC. So it is purposely done to have the full wave rectification. We don't need it to happen in the negative side. Yes. Yes. All good? Any question? So you have this. Okay, now how about this? I want you to do this one. This we call the Winston bridge. So I want you to do this. Think and do this one as well, okay? I'll give you time. Input is the sinusoidal and I want you to draw the output. Input is sinusoidal like before, okay? So draw the output. Okay, what did you get here? What's that? How come you get one down? So when the current is going in this direction, current comes to this node and it is not going towards the reverse bias diode, it is going this way. Am I right? And it is again not going through this diode because it is again reverse bias. Am I right? It is going this way, so it's going like that, and it is coming to this point here. But can it go up? Current is not stopping at the start. Isn't it? Current can't go back to the start point. It should go in a cycle, isn't it? So it should go like this and finishing at here. Am I right? So that will be like this. And in the other one, if it comes in the other way round, it goes like this. And when it comes to here, it should go this way, again going like this. And when it comes here, it should go back to the top. So it should go like this. Make sense? So in that way also you have a downward current. So your output will be like in the previous one, like this. Agree? So always the current is downward, isn't it? It, like, this, you can have this is a separate circuit. You need to figure out wherever the diodes is, it can be 4, 5, whatever the number, you need to figure out. No, yeah, you need to figure out how it is happening. It is a circuit, isn't it? The previous one also gave us the full wave rectification. This one also giving us a full wave rectification. Am I right? Any question? No questions? Okay. Okay, now the calculation part. So we have to understand first the basic concept. So here, peak voltage, we call that the Vmax. Vmax is the peak voltage. RMS value means root mean square voltage. If you consider Vmax divided by root 2, that will give you the RMS voltage. RMS means the root mean square. Makes sense? And the DC voltage. So when you have, depending on your full wave rectification or half wave rectification, so if you consider full wave rectification, so you have your rectified one like this. To find the DC voltage, which can be taken from this, VDC is equals to Vmax divided by pi. 2 Vmax divided by pi. Pi, you know, the number, the symbol that you have in the calculator, 3.14. So you can find the VDC for full wave rectification using this equation. And if it is half waves like this, if your rectification is half wave, then your DC current, DC voltage is less because it's only half. So this will be Vmax divided by pi. So twice is, you can have a twice voltage in the full wave rectification than the half wave. Does that make sense? So in questions they are asking you to get the we'll do questions in the tutorial. Okay, so get this output signal and find the Vmax, sometimes find the Vrms, sometimes find the DC voltage. So we need to know these relationships. Are we good? Okay, so we don't have any questions. We are not going to do any questions with the previous one, but we have questions in our tutorial. We are going to do it on Thursday. Okay, so the theory, the summary of the things that you need to know the symbol of a diode. It will look like this. You need to know that it has two configurations, reverse bias and forward bias. It is really important to understand whether the diode is in the forward bias or the reverse bias. Then it is like a switch. When it is in the forward bias, it is a closed switch, and when it is in the reverse bias, it is an open switch, so it not let the current to pass. And the voltage, ideal condition, voltage across the diode is 0. In the silicon diode, the voltage across the diode is 0.7, and we have discussed about these once few minutes ago. And this we call the half wave rectification, and this we call the full wave rectification. Are we good? So we will be doing more questions in the tutorial with the last part using these equations as well. You guys have any question? Any question? No, there are, if they say ideal situation, then there is no voltage across the diode. If you have a silicon diode, you have a voltage drop across the diode as 0.7. No, you in your syllabus you always get ideal or the silicon. Yes. Are we good? Any question? No questions? Okay, we'll wind up.